Hey, don't let the quarantine haircut fool you. It's Professor Jared Rathel here. In this short video, we're going to be applying what you just learned about radiometric dating to think about the age of our beloved third rock from the sun, planet Earth. So remember when Darwin was formulating his profound idea, many in Europe still believed that planet Earth was a mere 7,000 years old. The concept of deep time, first proposed by Hutton and then Lyell and embraced by Darwin, was truly radical. But the development and application of radiometric dating by Ernest Rutherford and Bertram Boltwood in the early 1900s would ultimately demonstrate just how mind-bogglingly old this solar system is. So in the Scientific American video that you just watched, the supplemental video materials, you learned that the unstable version of carbon, carbon-14, with its 8 neutrons, is going to radioactively decay at predictable and measurable rates. Every 5,730 years after a living carbon-based organism, like you and I and every other living thing on the planet dies, 50% of its unstable C14 will be lost. So you can measure the amount of C14 that remains relative to the normal C12 to determine how long ago the organism died. Radiocarbon dating is a wonderful tool when you're trying to estimate the age of a smilodon, the saber-toothed cats that have been recovered from the La Brea tar pits in Los Angeles. There have been over 3,000 different smilodon individuals that have been recovered, dating between 10,000 and 40,000 years old. Radiocarbon dating works great when we're talking about lubia. And I will tell you the amazing story about this baby woolly mammoth who died 41,800 years ago in my final Walk on the Wild Side video as part of our ecology unit. Again, her age was determined using radiocarbon dating. And finally, meet Otzi, the Iceman, recovered in the mountains in the Italian Alps in 1991. Radiocarbon dating revealed that he had been frozen in ice for 5,300 years. So this was a Neolithic hunter. So Otzi had defensive wounds. His right hand had been badly injured from grabbing something sharp, presumably a knife. And then he also was found with an arrowhead in his left shoulder. So this was probably an act of homicide, an ancient homicide. Radiocarbon dating is a wonderfully precise tool for dating organisms that died less than about 60,000 years ago. Out beyond 60,000 years, there's simply not enough of the unstable C14 remaining to make estimates with any confidence. Thus, when we're thinking about very old things like our planet and objects in the solar system, we can use the same chemistry, just different elements. So we use the predictable and very, very slowly radioactive decay, stepwise decay of uranium-238, big element 238, uranium, into lead-206. The half-life from this chain of decay is gulp 4.47 billion years, right? Compared to 5,730 years with carbon-14. There's also uranium-235, which is slightly smaller in mass, and its half-life is 703 million years. So Carl Sagan, hopefully you recognize that name by now, famously said, extraordinary claims require extraordinary evidence. So, what evidence do we have for an ancient planet Earth? So, using uranium lead radiometric dating techniques, like we've just discussed, and analyzing single atoms extracted from tiny zircon crystals from Western Australia's Jack Hills, researchers have confirmed that this crystal that you see before you is the oldest rock fragment ever found on planet Earth, dating at 4.375 billion, that's billion with a B, years old, plus or minus 6 million years. Over 50 years ago, on July 16th, 1969, at 4:17 p.m. Eastern Standard Time, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin landed their lunar module with only 30 seconds of fuel remaining on Earth's moon. Armstrong radios, Houston, Tranquility Base here. The Eagle has landed. At 10:56 p.m., Armstrong is ready to plant the first human foot on another world. With more than 500,000,000 people watching on television back on planet Earth, he climbs down the ladder and he proclaims, "That's one small step for a man and one giant leap for mankind." Aldrin joins him shortly thereafter and offers a simple but powerful description of the lunar surface: magnificent desolation. Aldrin and Armstrong explore the surface for 2.5 hours and they collect 21.55 kilograms. That's over 40 pounds of rock samples. They leave behind on the moon an American flag, a patch honoring the fallen Apollo 1 crew, and a plaque on one of Eagle's legs. It reads, "Here, men from planet Earth first set foot upon the moon. July 1969 AD. We came in peace for all of mankind." It's 50 years ago. Might be time to go back. So those samples of moon rock, again, using uranium lead dating techniques, dated between 4.44 and 4.51 billion years old. Why? Why would the moon date approximately the same as the oldest rock on planet Earth? The giant impact hypothesis, sometimes called the Big Splash, suggests that a Mars-sized planetesimal, this giant object, planet-like object named Theia, collided with a proto-Earth, creating this debris ring around the planet, which then condensed to form our moon. The collision was so powerful, it's what created the 23.5-degree tilt. It's what pushed the Earth onto its axis, and it's the reason why we have seasons. What's the evidence for this? The moon's oxygen isotopic ratios, it's like signatures in the rock. They seem to be essentially identical to those of planet Earth's, and the odds of that happening are, minute. So what that means is the Earth and the moon are essentially made from the same stuff. And like rocks on Earth, rocks on the moon date at about 4.5 billion with a B years old. Finally, did you know that the world's best preserved meteorite impact site on planet Earth is just 37 miles outside of Flagstaff, down to the southeast of Flagstaff? Originally called Barringer, now renamed to Meteor Crater. It's the spectacular result of a collision that rocked the American Southwest approximately 50,000 years ago with energy of more than 20 million tons of dynamite. The remnants of this meteorite, the Canyon Diablo meteorite, dates from 4.53 to 4.58 billion years old, giving us yet another age estimate for the formation of our solar system. So based on uranium-lead radiometric dating of crystals, zircon crystals recovered in Western Australia, as well as gneiss rocks, and that's GN, gneiss with a G, from northwestern Canada, samples of moon rock recovered on the Apollo 11 mission, as well as fragments from the Diablo meteorite. Based on all of those estimates, our best scientific estimate for the age of planet Earth is 4.54 billion years old, plus or minus 50 million years. Just going to let you know, for those of you that are watching the lecture, that's just the first problem on your assessment this week. That plus or minus is what we call the standard error. Remember, in science, we always attempt to quantify our uncertainty. And we do this by using repeated measures. So the standard error denotes the precision in our estimates, how repeatable those estimates are. And considering we're talking about aging an object that's billions of years old, plus or minus 50 million years, that's not too bad. Okay, now that we've established that planet Earth is 4.54 billion years old, let me welcome you to the third unit in Biology 182, the evolutionary history of life on planet Earth. So we have a lot of ground to cover in a very short amount of time. We'll talk about it in the next lecture, but life shows up about 3.5 billion years ago. So we've got to cover 3.5 billion years of history in 1 week if you're in an 8-week section, and 2 weeks if you're in a 16-week section, but it is possible. And so to demonstrate that, here's where we're going. Here's what life would look like, the history of life would look like if it were compressed into a 24-hour day.
Life. With an estimated 3.8 billion years of existence and evolution on Earth, it's an odd thing indeed. So how did we get here? And what would the Earth's 4.5 billion year timeline look like compressed into a normal day of 24 hours? The story begins early in the morning, around 4 a.m., with the rise of the first simple, single-celled organisms. However, these organisms are destined to spend quite some time alone. At 1 p.m., a simple cell engulfs another, creating a symbiotic relationship and the first eukaryotic cells, or cells with internal organs. At 6:30 p.m., these cells begin to form colonies, and thus the first multicellular life develops. But it isn't until 8:30 p.m. that sea plants appear, and 20 minutes later we suddenly see animal life erupt in an explosion of inventiveness. Jellyfish, the first true vertebrates, trilobites. Incredible diversification begins to take place, and just before 10 p.m., plants begin to appear on land, followed by land mammals. By 1024, the Earth is covered in carboniferous forests, and the first winged insects appear. Many reptiles dominate the land with less than an hour left, but a mass extinction event allows dinosaurs to storm the scene and remain until 11:41 p.m. when they too suddenly vanish. And so begins the age of mammals. In the last few minutes, apes split from the old world monkeys, and with only 1 minute and 17 seconds left before midnight, humans emerge. All of the recorded human history fits within a few seconds, an individual life lasting barely an instant. All a culmination of 3.8 billion years of life.